Okay, yes, we are still here. We want to talk about the classification error measures of fitness for trees. We know what cross entropy is. Now let's see how it plays a role in trees. Okay, so imagine we have k classes. It's a classification problem with k classes. And we have for a tree, remember, we stratify the space into regions, right? So different regions, and so that within each region most of the observations have the same label. The whole point is to find the regions where observations tend to have the same label, so that if another new observation comes and it's close to them, we predict its label to be the majority of that region. So regions play a key role because regions tell us how to split the feature space, and therefore we'll know in which region which class is the majority. And for that purpose, we need to quantify the number of observations that fall in each region. Little m is one of the big M regions, and xi in Rm. So this is not the real line. Sorry, I shouldn't have put this extra line here because then it will indicate that this is the real line. But no, I mean region M. So all the points that are in region M, essentially this is the set of points that fall in region M. And then if we put these two lines, so the size of this set is nm. So in region M, we have nm observations. And then the proportion of observations in region M that have labeled little k as their class, we call it p hat mk. So we stratify the space right into these regions for the tree, and for each of these regions, let's say region M, we see how many observations have a label little k. So that will be p hat mk, and essentially it is the total number of observation in region is big N M, and here we are summing over all the observations in region M, but only those for which label their corresponding label is k. So this is an indicator function. This indicator function is 1 when yi is equal to k, and it is 0 otherwise. So as we go through the points in region M, we look at their corresponding label, and if that corresponding label is little k, then we will have a 1. So essentially this summation here is counts the number of points in region M that have label little k, and little k goes from 1 to big K. Okay, so a little bit of notation. It's important notation because we are going to use this this proportion, or say probability, in our measure. And essentially what we like is that the region is pure in the sense that most of the points have the same label. It doesn't matter what that label is, it's just to have the same label. So most for p hat mk, for most of the k's is small, near 0, and then for one of them is close to 1. That would be great. That means that the majority of observations in that region say the same thing. They have the same label. That means that's a good region. Okay, so intuitively we want regions for which the probabilities is peaked, meaning that most of the probabilities for most of the labels is near 0, and then one of them is close to 1. That would be a great region. And we want to see whether we can quantify, find a quantifiable way to express this intuition here that we just said. So how can we do that? We need another character in our story, which is k parentheses m, essentially this k parentheses m is saying that what is the majority label of region M? What is the majority label of region M? Well, it is the label, which is a number between the class between 1 and capital K, but it is the data J for which P hat Mj is the largest. So we are going through all the labels in class in region M, and then we are going to pick the majority. We're finding the majority. So little k m is the majority label of region M, and any data point that will fall in that region will be classified as k parentheses m. Okay, excuse me. So there are different measures of node impurity in region M. We call them Qm of T. T is the tree. M refers to the region, and Qm3 is the node impurity. And so for each region, we have a measure, and then we're going to sum over all the regions, and that will be our total loss. So one is the misclassification error. Misclassification error is obviously 1 minus p hat m k of m. So if we are saying, okay, what is the proportion of the majority in region M? What is the proportion of majority in region M? Let's say it's 0.9. So 1 minus 0.9, it's 0.1. 10% error in that region. Again, I just want to emphasize that these measures that we are talking are per region. In the end, we have to sum over all the regions. But this is per region. Now the Gini index is just saying, okay, sum over all the proportions. Well, now the problem here is that this measure of error only takes into account what's the majority. It doesn't take into account how the minority are distributed. Do we have one minority, or do we have many minorities? Okay, and the Gini index is a little bit more sensitive to that. Essentially, the Gini index is largest when p hat mk's are as smallest when these are close to 1. Again, peakedness. The peakedness of this, instead of looking at only the maximum, it sums over all the classes. And if most of the p hats are close to 0, then this quantity will be 0. And then if one of them is close to 1, this will be also 0. So if it's peaked, then the Gini index is low, so that the cost is low. But if these probabilities are close to each other, then and they're away from 1 or 0, then this becomes larger. So this is also the variance. Remember, p times 1 minus p, so it's the variability. Finally, we have the cross entropy or deviance, which is the sum, negative sum, little k to capital K, p hat mk log p hat mk. Again, this is for region M. For region M, we look at the proportion of each class. That will become p hat mk, and then we do a negative p hat mk log p hat mk. Again, I want to emphasize that this is for trees. This is different from what we have said about in general classification problems. What is a reasonable loss for them? That's a different story. So for two classes, capital K is a big K is 2. Big K is 2, and let's say P is the proportion in the second class. Okay, then the error is 1 minus max P, 1 minus P, Because if P is the proportion in the second class, then 1 minus P is the proportion in the first class, and whichever is largest will make the majority, so 1 minus that will be the minority. So that is our measure of error as a function of P, which is 1 minus max P and 1 minus P, and if you plot that, that's what it is. So this is on the vertical axis we have the measure of error. On the horizontal axis we have P. P goes from 0 to 1, and for misclassification error it is 0 when P is 0, it is 0 when P is 1, it is largest when P is 50-50, so it goes up and down. So if you have a region where half of the data points are in one group, another half or another group, then this is the largest, that's the worst thing that could happen, because it's the most diverse region, and that defies the whole purpose of segmenting the space. Okay, so this green line, essentially green broken figure, is just plotting 1 minus max P and 1 minus P as a function of P. The Gini index becomes 2P times 1 minus P. Comes like this blue one. And then the cross entropy becomes a negative P log P minus 1 minus P log 1 minus P. So the book calls this node impurity. Node impurity. Node in the context of trees is a region. So when we say node, it's the same thing as saying region. And for each region, for each node, we want to have a loss function. The loss function in this context is impurity, because it measures the opposite of diversity in that region. The whole point of segmenting the space into regions is to get rid of the diversity, to segment points that have the same label more or less together, and that's what we are trying to measure. And this is from the ESL book. You can figure 9.3, so you can read. I recommend you read the discussion around it. So cross entropy and Gini index is more sensitive to changes in the node probabilities than the misclassification rate. Why is that the case? Because at the end of the day, the misclassification error rate only takes into account what is the probability of the majority class. Whereas the Gini index and cross entropy, while it is heavily influenced by the probability of the majority index, it also takes into account the probability of those other classes which are not majority, and it sums over all the probabilities for all the classes, whereas the Gini index only is a function of the majority class. Sorry, the misclassification error is only a function of the majority class. So let's look at an example. A two-class problem. Class 1, we use blue for class 1, and we use red for class 2. And imagine we have 400 observations in each class, right? And now we're going to consider different ways. There are two cases which we are consider. Imagine this is our feature space. This is just a caricature, and we have two regions where one region is consists of 300 blues and 100 reds, making the majority class here blue, right? And region 2 consists also of 400 observations, 100 of them blue, 300 of them red. So region 1 will be blue, region 2 will be red, right? Now, a slightly different split would give you region 1 and region 2 again, where there are 200 observations in region 2, all of which are blue, and it would give you a larger region 2 with 600 observations. Not the region is not necessarily larger, but there are more data points in it. Okay, so disregard the relative size. I'm just splitting the space arbitrarily. Focus on the numbers. So here are 600 observations, 400 of which are red, making again still red the majority. But now let's look at this. How many mistakes do we make here? 200, right? How many mistakes do we make here? 200. No, no. Forget about that. I made a mistake. How many mistakes do we make here? 100, right? We have 400 observations, and given that this whole region will be labeled as blue, there are 100 mistakes here, and the same applies for region 2. We have 400 observations. The majority is red, so we have 100 mistakes. So 100 plus 100 divided by 800 observations, right? So the total error rate for this split is 200 divided by 800 total, and for each region is 1/4, right? Now, if you look at this, the errors, the total number, I mean, this region is labeled, will be called blue because the majority is blue, and this region, the majority is red, so it'll be red. So, but since there are no reds here, we don't make no mistakes here. But since there are 200 blues, we make 200 mistakes. So 200 out of 800, again, 0.12. So the error rate, the misclassification rate for case 1 and case 2 are the same. Okay, so now that we have the misclassification rates, I would like to calculate the cross entropy for each region and for each case. And for that, we need to find the majority for each region, obviously. So p hat 1, 1. Just look at this again. Case 1, right? P hat 1, 1 is blue is class 1, so it's 300 over 400, right? And then p hat 1, 2 is just the complement of it because we're talking about region 1, and for region 2, it's the total opposite. P hat 2, 1, it's for region 2. What is the proportion of 1s? 100 out of 400. So class 1, class 2, region 1, region 2. Km, what is K1? Is 1, right? Because the majority of region 1 is 1. K2 is also 2 because the majority of region 2 is 2. This is just an accident here, happened to be the case. But just so you know what's the meaning of Km again. Now for class 2, if we create the same table, well, for region 1, we have 200 observations, 200 of them are blue, so 2 out of 200 out of 200. And then here we have 200 out of 600. And then we have 400 out of 600, right? So these are the probabilities. So again, what I'm trying to do is this. Let me just give you a little bit of context here again. That we have two cases. the same data, the regions are slightly different. Here we can see that the node purity, I mean, we expect this to have a slightly lower loss than this one, because this one seems better, because there is a essentially we have a region with the majority being 100%, and we have another region which is not 100%, but is 2/3, which is okay. Whereas here we have two regions, both of them are 75% majority, right? So two 75% majorities versus 100% and 66%. So we would think that this is better. Therefore, case 2 should have a lower cross entropy, whereas misclassification error is unable to distinguish between these two cases. So I'm trying to show you the subtle difference that cross entropy makes in comparison to misclassification rate, which just doesn't take into account the distribution of the minority group in each region. So anyway, these are the numbers. I leave the notes so you can spend some time just deducing them and figuring out. This is very precise. So if you follow these definitions and the beginning of the video, you should be able to figure this out. This is pretty straightforward, but it may look tedious, but if you do it once, it will all fall into place. And if you do the cross entropy, the cross entropy for region 1 is minus p hat 1 1 log p hat 1 1 minus p hat 1 2 log p hat 1 2. This is for region 1, and this is for region 2. And then we have the numbers, right? I'm just putting them in here. And for case 1, the cross entropy is 1.62. This is in log basis 2. So what I did was I did it here. So this is, just ignore this. Okay. So this is one of them. This is the other one I did. Okay. And the convention is 0 log 2 is 0. Again, the reason I divide here by log 2 is because I want things to be in a basis of 2 log 2, because it's a binary classification problem. It is customary to do everything in the basis 2. So this is essentially what I wanted to get across. A lot of details you need to revisit on your own, but it's all here. And the take-home message is that when it comes to using a tree or fitting a tree, it is preferable to use cross entropy or even the Gini index than the misclassification rate as a measure of loss. Cross entropy for classification is more sensitive to changes in the node probability. So in general, I recommend cross entropy in comparison to misclassification error. And if you look at the discussion in the Elements of Statistical Learning book, around figure 9.3, so what I discussed was essentially mostly from this part of the book. So I recommend you read this part on your own, 309, and it goes over everything I said.